All right, yeah, thank you. Well, thanks everyone for coming, and thanks to the organizers for putting together this wonderful workshop and for the chance to speak here. This is based on joint work with Ashley Adams and Jessica Stryker. This is a picture that I took of my collaborators taking a picture of a wall. So I'm going to talk about combinatorial billiards. This, I guess, is sort of like a new subfield of dynamical algebraic combinatorics. Some might call it a budding subfield. And basically, the idea is we have some kind of billiard system, like what people would study in classical dynamics, but it's going to be very rigid and constrained and, in some sense, maybe discretized. And we're going to think about it combinatorially. So in this talk, I'm going to focus on the affine Weyl group AN-1 tilde, which is also the affine symmetric group SN tilde. I can think about the elements of this group as these little alcoves in some kind of affine hyperplane arrangement that looks something like this. So it'll be in an n-1 dimensional space. Here n equals 3, so I get this picture, and the alcoves are these little triangles. In general, the alcoves will be n-1 dimensional simplices. Now I'm going to write S1 through Sn for the simple reflections of this group. So the Dinkin diagram just has S1 through Sn listed around clockwise around a cycle. And if I'm in one of these alcoves and I multiply by a simple reflection on the left, that just has the effect of moving to an adjacent alcove. And it turns out that if you multiply by the simple reflections in this order, going S1, S2, dot, 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 Sn, S1, S2, dot, 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 Sn, and so on, you're basically just going to move along in a straight line. So here I went S1, S2, S3, S1, S2, S3, S1, S2, S3, and so on. And you can see I'm just moving along in a straight line. Now, if at some point I decide to skip one of these simple reflections, that will have the effect of reflecting against one of these hyperplanes. So here I did S1, S2, S3, S1, S2, S3. Then I decided to skip the next S1, but then I continued going S2, S3, S1, S2, S3, and so on. You can see I basically reflected against this red mirror here. OK, so people have studied billiard systems for a while with reflections, and you can imagine, OK, maybe the beam of light could pass through a hyperplane or it could reflect. But we thought, well, what if there was a third thing that it could do? What if it could refract? So here, the beam of light is going to refract in a way that it bends as it goes through this hyperplane. And we'll assume that the new direction that it points is the opposite of the direction it would have pointed if it had reflected. So if it had reflected, it would be going that way. So instead, it goes the opposite direction. In physics terms, we would say the coefficient of refraction is -1. So that's basically saying that these angles are the same there. So the coefficient of refraction is -1. OK, so we came up with this definition of refraction, but then after doing some Googling, we found that over the last 10 years or so, there's actually been this flurry of attention in the dynamics community looking at the exact same thing from a dynamical point of view. So they study what they call refraction billiards, and they just do like these billiard systems with this same notion of refractions. Sometimes this is also called tiling billiards. And so I'm going to distinguish 3 different types of hyperplanes. I'll have windows, mirrors, and meta lenses. So a window just allows the light to pass through. A mirror causes the light to reflect, and a meta lens causes the light to refract. So the reason it's called a meta lens is because, OK, well, in the real world, you actually can't have a negative coefficient of refraction. Like Snell's law or whatever it is says that actually the coefficient of refraction has to be positive. That would correspond here to saying that the new direction of my beam of light should be somewhere below the horizontal axis. Except apparently, about 20 years ago or so, there was this breakthrough in physics or material science where they found or invented these things called metamaterials, which apparently do have negative coefficients of refraction. So apparently, you can have something like this. I'm not a physicist, so I don't really know what a metamaterial is. I don't know how to make one, but the point is that's why we're calling this a meta lens. It's like a lens because it refracts, but it's meta because it has this negative coefficient of refraction like the metamaterials. OK? OK. So we want to do this combinatorially. So I have my simple reflections here. And the idea is if I want to do a refraction, I just apply the simple reflection to go through that hyperplane. But then I reverse the order in which I continue applying simple reflections. So here I went S1, S2, S3, S1, S2, S3. And then I want to do a refraction. So I do S1. And then I start going S3, S2, S1, S3, S2, S1, and so on.
Sorry, that's not clear. Why did you start with S3? I mean, you could have started S2, S1, S3.
Oh, yeah. So I just mean I've done the S1. And now I'm going to start going the other way around the Dinkin diagram. If you imagine I'm sort of going around the Dinkin diagram clockwise, then I do my refraction by applying the simple reflection. And now I start going the reverse, counterclockwise around the Dinkin diagram, okay? And then if I refract again, then I start going clockwise again, okay? Okay. So another nice thing about the affine symmetric group is that you can write it as a semi-direct product of the finite symmetric group Sn and a certain lattice called the co-root lattice, which I'll denote by Q check. If you take this Euclidean space here and you mod out by the co-root lattice, well, you're going to get an n-1 dimensional torus. So here, this is a picture of a two-dimensional torus where I've identified the opposite sides of this hexagon. So this is like actually topologically a torus. If you want to think about this combinatorially, you can think of the elements of the affine symmetric group as affine permutations. And each affine permutation has a window notation. And if you reduce the window notation mod n, that just gives you a permutation. So that's what this map is doing on the combinatorial level. But in terms of this picture, basically I've colored the alcoves different colors so that two alcoves have the same color if and only if one of them is a translation of the other by a co-root vector. And then this quotient is just identifying alcoves of the same color. So I get this picture here. Okay, now I also have this beam of light that's moving along and it passes through the window and then it refracts and reflects and then it passes through and reflects again and it moves along. It sort of looks like a heart monitor here. And then what I'm doing is just projecting this into the torus. So now I have this beam of light that is moving along in the torus and it's reflecting or refracting or passing through based on whether it's hitting a toric window or a toric mirror or a toric meta lens. So I've projected my affine Coxeter arrangement into the torus to get this affine or this toric hyperplane arrangement with toric hyperplanes. Except, okay, in order for this to make sense, I need each toric hyperplane to have a well-defined material. And by material, I mean it should be either a window or a mirror or a meta lens. And in order for that to make sense, I want to assume that for every toric hyperplane, all of its pre-images under the quotient should have the same material. Okay? So I'm going to make that assumption in what follows. But this is really equivalent to just saying that in this affine picture, I want parallel hyperplanes to have the same material. So for example, you can see all of the horizontal lines are red, and so they are all mirrors. Okay? Okay, well now, okay, so I have the same picture from before. And this is just a blown up version of the torus. The little toric alcoves here correspond to the permutations in Sn. So there are 6 of them here because there are 6 permutations in S3. And I've written them as labelings of a graph. So I have my little path graph here with vertices 1, 2, 3. And this is a labeling. Well, this is 1, 2, 3, so that's the identity. But here I have like 2, 3, 1. So that's the permutation 2, 3, 1. So let me explain why I'm drawing this graph. Well, this is basically going to determine the materials of my hyperplanes. I'm going to choose a graph G with vertex set bracket n. And then I'm going to partition the edge set E into these 2 subsets that I'll call E-flect and E-fract. So this symbol is called E-flect. This symbol is called E-fract. And the elements of E-flect are called reflection edges. The elements of E-fract are called refraction edges. So this will determine the materials of my hyperplanes because every hyperplane is parallel to exactly one hyperplane in the finite braid arrangement. And the hyperplanes in the finite braid arrangement are of the form xi equals xj for some numbers I and j between 1 and n. So what I do is I say, well, if I and j are not adjacent in this graph, then I just make the corresponding hyperplane a window. And if I and j form a reflection edge, then I make the hyperplane a mirror. And if I and j form a refraction edge, then I make the hyperplane a meta lens. Okay? And then, again, because of this condition that parallel hyperplanes have the same material, this will uniquely determine the materials of all of the affine hyperplanes here, which then determines the materials of my toric hyperplanes. Okay? Okay, but now I want to combinatorialize this. So basically, we can think of our beam of light moving around in the torus, but we can think of it in a step-by-step procedure, like when we had these simple reflections that were just moving along step by step. So this is like a step-by-step discretized version of the heart monitor beam of light that I had before. And so I want to just describe this in terms of a combinatorial dynamical system. So the point here is I'm going to define some combinatorial objects, and I'm going to define a bijection from the set of these objects to itself. And that dynamical system will encode my dynamical billiard system in the torus with reflections, refractions, and passing through. Okay, so well, what are these objects? Well, it has two pieces. The first is just a permutation, which I'm viewing as a labeling of my graph, and that's just telling me where my beam of light is, right? So it's saying what alcove is the beam of light in. And then the second piece is a cycle graph with the vertices 1 through n listed around clockwise. And I'm going to place a stone on one of the vertices here, and the stone will point either clockwise or counterclockwise. Okay, so in this example here, the stone is sitting on the 1, and it's pointing clockwise. I don't know how well you can see the arrow, but it's pointing clockwise. And that data is encoding the direction that the beam of light is facing in the torus. There's a way of getting it from that. Okay, so now I just want to define how do you go from one state to the next state in this dynamical system. Well, I'm going to look at the stone. It's sitting on some vertex, and it's pointing toward another vertex. So here it's sitting on the 1, and it's pointing toward the 2. So I look at those labels. I look at the labels 1 and 2 in my labeling, and then I ask, okay, are they sitting on non-adjacent vertices, or are they sitting on a reflection edge, or are they sitting on a refraction edge? And depending on which of those cases I'm in, I have a different rule. So in this case, the 1 and the 2 are sitting on non-adjacent vertices, and the rule in this case is that I should swap those labels, and I should move the stone one step in the direction that it's pointing. So you can see I swapped the 1 and the 2, and I just moved the stone one step clockwise. Okay? So let me do this example now. Now the stone is sitting on the 2, and it's pointing toward the 3. So I look at the labels 2 and 3. They're sitting on a refraction edge. So the rule in this case is I swap those labels, again, the 2 and the 3 here, and then I just reverse the orientation of the stone. So it was pointing clockwise, but now it's pointing counterclockwise. Okay? Now one more example. Okay, so the stone is sitting on the 2, and it's pointing toward the 1. So I look at the labels 1 and 2. I see that they're on a reflection edge. In this case, the rule is that I do nothing to the labeling, and then I move the stone one step in the direction that it's pointing. And it's pointing counterclockwise here, so it moves counterclockwise. Okay, so I just have these 3 rules, and I apply them. This gives me some kind of dynamical system. And our goal is we want to understand the orbit structure of this dynamical system, which will then tell us about the orbit structure of this billiard system in a torus. Okay?
Can I ask, why are your pictures above the triangles, not also triangles? Like, why is it, shouldn't there be a non-edge from 1 to 3, a window edge?
Oh, like why is there no window edge there?
Yeah.
Oh, I'm just not drawing. You could imagine I have window edges and they're just not drawn.
Okay.
Yeah, it's just a convention. Yeah. Okay. So this is just basically a symbol-heavy way of explaining what I had on the previous slide. Again, I have my graph G with vertex set bracket n. I have my edge set partitioned into these 2 subsets, eflect and efract. Psi is going to be my set of combinatorial objects. So I can encode that by saying, well, it's a permutation in Sin, together with a placement of the stone on one of the vertices, and I'll encode that by an element of Z mod in Z. So that's just saying, where do I place the stone? And then the plus or minus 1 is encoding whether the stone is pointing clockwise or counterclockwise. And then theta is just this bijection that I defined on the previous slide. It's what takes me from one state to the next state. And you can define it with these 3 cases with symbols, but let's not worry about the symbols. It's just what I had on the previous slide. Okay? Okay, so our goal was to understand this dynamical system, and there are some cases where we do this. One is when the graph is a tree. So if G is a tree, then I can partition the vertex set bracket in into these 2 subsets, x1 and x minus 1, so that every refraction edge has endpoints in different subsets, and every reflection edge has endpoints in the same subset. And then I define chi of G eflect efract to be the absolute value of the difference of the sizes of these subsets. Let me give an example. Okay, so here I have some tree. It has refraction edges, which are in teal, and it has reflection edges, which are in red. And I've colored the vertices green and purple. This just corresponds to my 2 subsets, x1 and x minus 1. And you can see that I've done this so that every refraction edge has endpoints of different colors, and every reflection edge has endpoints of the same color. And so then you can compute chi. This chi number here is just the absolute value of the number of green things minus the number of purple things, which in this case is 2. Okay? And so our theorem is that, in this case, actually all of the orbits of theta have the same size, which I think is already kind of surprising. And we can tell you what that size is. It's n squared times n minus 1 divided by the GCD of n and this chi number that I just defined. So this is exactly determining the orbit structure of this map when G is a tree. We also proved something more general for forests. It's just a little bit more complicated, so I'm not stating it here, but it's basically something like this. Okay. Let me give a small example of this. So here I have my path graph with 3 vertices. It has 1 reflection edge and 1 refraction edge. You can easily compute that this chi number is 1. So if I plug into my formula, I get 3 squared times 3 minus 1 divided by 1. That's 18. So this theorem says that all of the orbits of my map theta will have size 18. And in this case, okay, I just chose some element, and then I did my map 18 times, and I get back to where I started. Okay? And if you start anywhere, then after you do it this 18 times, you'll get back to where you started. Okay? Okay.
So why were the 2 stones in the last picture?
So, oh, that is wrong. Yep, okay. I wonder if that's in our paper. Okay. No, I should check that. Okay, hold on. Yeah, okay.
So, cool question. So every orbit is a path in the torus, right? So it's they'll shift in the same direction
Yeah.
in the plane, or like what's the homology of those orbits?
Oh, that's an interesting thing that, yeah, I mean, I don't know in general. Like it might just get back to where it actually started, or maybe it'll go off to infinity. This is something I think would be interesting to consider. Yeah. Okay, the other case that we handle is cycle graphs. Here we assume that there are an even number of refraction edges. And in this case, we give a simple way of computing the sizes of the orbits of theta. It's not terribly complicated, but it's a little bit too much for what I want to explain here. So I'm just going to say there is a way of doing this. There are a couple nice cases. One is when there are no refractions at all. In this case, this map that I've defined, this dynamical system, is really the same thing as something that I defined a few years ago called toric promotion. And we didn't previously understand the orbit structure of toric promotion for a cycle graph. So this is new even in the case of just toric promotion where there are no refractions. And then the other really nice case is when there are only refraction edges. Okay, so here I'm going to assume G is a cycle graph with even size, and it has only refraction edges. And so for the last few minutes, I'll tell you the answer in this case. Okay, so let me just fix a little bit of notation with Young tableau. Here, lambda is a partition of some number capital N. B of lambda is this quantity where you sum up I minus 1 times the ith part. A descent of a standard Young tableau is just an entry I that is higher up than the entry I plus 1. And if you sum up the descents of a standard Young tableau T, you get what's called the major index of T. And then you can define this generating polynomial for the major index statistic, which has this nice Q hook length formula like this. So this generating function is f lambda of Q. I'm also going to define f lambda sub in divides maj to be the number of standard Young tableau of shape lambda such that the major index is divisible by n. Okay, if you want, you could compute this with some kind of sieving polynomial thing, but if you want to think about it combinatorially, it's just the number of standard Young tableau of shape lambda where the major index is divisible by the number of boxes. Okay. Okay, this is what I had on the previous slide. And then the theorem says, okay, let's let G be a cycle graph with an even number of vertices, and it has only refraction edges. In this case, the sizes of the orbits of theta are all of the form d times n minus 1, where d is a divisor of n minus 1. And okay, so this already says that the orbit structure is very constrained, but then if you want to know like exactly what the orbit structure is, like for each d, how many times does it show up, that's encoded by this second part of the statement, which says that for every integer k, the number of elements of psi, remember psi is our set of combinatorial objects, the number of elements that are fixed by theta to the k times n minus 1 is this thing. So it's 2n squared times n minus 1. You sum up over partitions of n minus 1 of the number of things with major index divisible by n minus 1. And then you plug in this root of unity for the q in this f lambda of q. So this is e to the 2 pi I k over n minus 1. OK, so it's something. You can write it down. And this is completely determining the orbit structure. I'll say that this is an instance of something called the cyclic sieving phenomenon, which was introduced by Reiner, Stanton, and White. But yeah, it tells us our orbit structure.
Is it an instance of cyclic sieving, like you prove the theorem and then you look at it and it's like, oh, cyclic sieving?
Well, it's sort of like we have a description and then we basically go to, I mean, I can go to the thank you slide. But yeah, basically we sort of cite a different paper that has a cyclic sieving result and we sort of import things from there with some tweaks. Yeah, but anyway.